All right, here we go. We're going to talk about basic triangles. Forget that word that's on the board. We're not going to use that word at all. There it is again. We're not going to use that word. Those are cuss words. We're not going to use that word right there. We're going to find a right triangle. We are going to discuss the Pythagorean theorem, and we are not going to apply it very much. If you do this electrical stuff, then you need to do it by sine, cosine, tangent, not Pythagorean theorem. Pythagorean theorem is a shortcut that you can use sometimes, but it leaves you needing other information. Okay? And solve problems using sine, cosine, and tangent. That's mainly what we're going to do. Okay. Now, needless to say, Pythagoras was a really smart guy. He found what he was looking at was land. And because sometimes plots of land are not exactly square, he realized, okay, I could find out the area of this thing, even though it's kind of a triangle. As long as this thing's square down here, we'll just square this side, square that side, and the other side is squared equals to that thing. And we're not going to get into that. Okay? And when I write this formula, then I'm going to keep this thing covered up here. Give me my thing here. It's not going to, yeah, there we go. Okay, and when I do write this thing, I write h squared, not c squared, because it's the hypotenuse. And adjacent, I kind of like a squared, adjacent, and then I don't call this b, I call this o. O squared plus, oops, sorry. I got rid of my writing, which is probably a good idea also. Okay, let's go down to, okay. Trigonometric functions also describe the mathematical relationships to the sides and angles of a right triangle. Most important thing in this class, in my opinion, or one of the most important things in this class, is that right there. The relationships of the sides are the sine, cosine, and tangent. They are what we call functions. And we have, now this is drawn backwards to me, so we're going to draw it the other way. So this is the angle, and we're going to call this theta all the time. Angle theta. And if you draw a line through angle theta, the one we're considering it, we call this the side opposite. And you know that whatever's next door to you is adjacent to you. It's near you. So this one's adjacent. And this one is called the hypotenuse. Now the hypotenuse, this is a right triangle over here with its 90 degrees. The one that's opposite the 90 degrees is the hypotenuse, and it's always the longest one. And mathematically the largest number, unless we're talking about reciprocal functions, but we'll talk about that later. Okay? Okay, sine function. If we go back to our triangle, and we're going to start our mnemonic right now. Oh hell, another hour of agony. And we're going to start using that from now on. Oh hell, another hour of agony, and that's sine, cosine, tangent. And now you'll notice that spells out SOHCAHTOA. My old Indian friend put his toe in the water, SOHCAHTOA. And, okay. Now let's look at, again, this is the side adjacent, the side opposite. This is our angle. The one the opposite is the opposite. The one that's next to it is the adjacent. The one that's opposite, the 90-degree angle, is the hypotenuse, and it's always the longest. And oh hell stands for the opposite over the hypotenuse. Okay, so the opposite compared to the hypotenuse is the sine. Now, let's look at, well, we'll do that in a second. We can scale this up and we can scale it back down. We can make it bigger or make it smaller. But the relationship, the fractional relationship between the opposite and the hypotenuse is always the same. Oops, wrong way. Okay, so we have one. We have sine now. Now we have cosine, okay? The cosine is, oh hell, another hour. A over h. Okay, let's write that again. OH, oh hell, another hour of agony. Does that remind anybody of their homework? Oh hell, another hour of agony. Everybody reminds you of that? Reminds you of your homework? Okay, now the cosine is this one. Cosine of the angle is A over H. That means that if I'm looking at that triangle, I know those two sides. The cosine is that number divided by that number. It's that simple. It is that simple. Okay, and then you can simplify that down to a decimal thing after you've got a fraction, right? Because you all can turn a fraction into a decimal, right? Divide one into the other, you got a fraction, you got a decimal, right? Okay, now let's look at this. Let's draw my little triangle one more time. Actually, we're going to probably draw a lot more than that, but that's okay. Adjacent, opposite, my angle, this is my hypotenuse. Okay, and what is the cosine? A over H. The adjacent divided by the hypotenuse. Okay? Now, again, we can scale that up, scale that down, and there we go. Then we have the tangent. The tangent comes in handy sometimes. What's our formula again? Our mnemonic? Oh hell of agony. Oh hell, another hour of agony. There we go. I left something out. Sine, cosine, and now we have the tangent of agony. And the reason we need that's all, folks. The reason we need to remember O over A is so we put the right one on the top. The only thing difficult about the tangent is remembering to put the opposite on top. So the opposite of our triangle, our angle down here, this is our adjacent, and this is the opposite over, not the hypotenuse, the adjacent. The opposite over the adjacent. Okay? Now let's look at, if you're standing a ladder on a wall, you know that for every 4 feet you go up, you got to come out 1 foot. That's a relationship, right? But what if you don't want to go up 4 feet, you want to go up 40 feet? We can multiply this by 10, can't we? Make this 40. If we multiply that times 10 and we multiply this times 10, 40 times over 10 is still the same fraction as 4 over 1, right? 40 over 10 is the same fraction as 4 over 1. It just scaled up. And that's the same thing that happened here. We went up to 40 and 10 instead of 4 and 1. That's scaling up. So if we have the angle, we know the relationship between it. Once we have the angle, we know the relationship between any two sides, right? Oh hell, another hour of agony. And if we have any one side, that sets the scale for the whole thing. That sets how big is this triangle, right? Because once we have this 10 or the 40 or any other part, we've scaled it up or scaled it down to fit our needs. And that's really all this triangle stuff is all about. It's really fairly simple. Okay, so that's it. Believe it or not, now, as they say, the devil's in the details, though. It's the practice that we need to... Let me hit pause for a second and get a clear screen. Now, the problem with almost any kind of information you learn anywhere is, why am I going to need to know this, right? You don't have to lie to me, I know. You want to know, why am I going to need to know this? Well, first of all, let's say that you want to bend a piece of conduit to go over an obstruction. Let's say, you know what, I don't like that drawing now. Thank you. Let's say we have, say, a 15-inch obstruction. and we're coming along here with a conduit running along this deck. We want to kick up and go over this obstruction. We want to put a certain amount of bend in the conduit and then kick it back down to make it level again, and that's what's called an offset. So we're going to offset a conduit, right? Now we know we could look at this as a triangle, or I hope we know that. If we look at this, we can suddenly see an angle happening here. We can see our obstruction is our side opposite, right? Now, what if we decided on a certain angle ahead of time? Let's say we're going to pick 25 degrees. We're going to kick this conduit up 25 degrees. And I need to get over an object that's 15 inches tall. What am I looking for if I want to bend it here, and make it lay flat right on top of this obstruction? My hypotenuse. That's what I'm looking for. I'm looking for my hypotenuse because that's the marks between the bends. If I bend it one way, I go down to the other mark, I flip it over, and I bend it the other way, I have what's called an offset. Now, this is just one of the many uses for this kind of stuff, but I do want to point out that everything from now on has a purpose, okay? All the stuff we're going to talk about, this is just one of them. We're going to talk about motors in just a minute. Now, let's say that I've picked 25 degrees, right? Now, let's look at our oh hell, another hour of agony. Sine, cosine, tangent. And again, these are fractions. This number is a fraction that's equal to this over this, right? Now, we have one that has the opposite in it. So we know that we're looking for something that has the opposite, and we're looking for the hypotenuse. So it's got something we have and something we're looking for, right? So everybody pull out your handy-dandy TI-30X2S calculator. I'll give you a second to do that while we pause. Okay, now we're looking at the sine. And we can look up the sine by turning on our calculator. And we're going to just put in clear twice just to get all the junk out. And then we're going to hit sine 25, enter. And it's going to tell you the sine of 25 degrees. And that is what? Okay, so it's 0.4226. That was a fraction reduced down to a decimal, okay? And that's equal to O over H. Now, we know one of those, don't we? Which one do we know? We know the opposite. So let's just take the O out of here. Now let's, oh no, go away. Oh no. No, not going to do it. No, that's all right. We can do this. No problem. 25 degrees. Okay, and we're using sine. And that's 0.4226, thank you. And that's equal to, what was we're going over a 15-inch obstruction, right? So it's O, which are our opposites, is 15. That sets our scale over the hypotenuse. Now, I want you to realize that anytime we have A is equal to B over C, we can multiply both sides by C and divide both sides by A and wind up with C is equal to B over A. Everybody realize that, right? Okay, that was from the 3rd grade or 4th grade, 5th grade, 6th grade, somewhere in there. We don't know where it came from, but a long time ago. So that means that we can take these two and exchange them. That's all that means to you right now, right? So we're going to rewrite this, and we're going to say H is equal to 15 divided by 0.4226. And now you have 0.4226 in your calculator already, right? So what we're going to do is we're going to put in, we're not going to do anything else. We're just going to put in 15 divided by second function, answer, enter. We got the answer. Isn't that easy? 15 divided by second function, that's that little colored one up in the upper left-hand corner. Answer is the little dash down in the lower right-hand corner. And then hit enter. 35 what? Now, there's two problems with this answer. Okay? 35.49. That is the distance between. Now, we're going to come back all the way full circle back to the first week we started. When we first started this class, what did we talk about? Didn't we talk about converting decimals back to fractions and ballparking to the nearest 16th of an inch? Oh, no! So 35 inches, that's on my tape measure, right? How about 0.49 inches? Is that on my tape measure? No, but we know it's close to 5, right? Close to half an inch. Okay, we're going to go to eighths, and we're going to start talking about this now. We're going to go to eighths or sixteenths. An eighth is 0.125. And a sixteenth is equal to 0.625. And we talked about, whoops. We talked a long time about how we got there. That's 6. Oops. Can't write. So now, if we know that 1/16 is 0.625 and 0.50 is half an inch, what would happen if we subtracted 0.5? We take 0.5 and subtract 0.0625. What number do we get? 0.4375. You know what? That's actually a little too far, isn't it? 0.50 was a little bit closer, wasn't it? 0.43, this is 0.49. So actually, half an inch is less than a 16th away from the right answer. How wide is a 32nd of an inch? Anybody got a pencil on them? The end of your pencil may not be as narrow as 32nd of an inch. So what you're saying is go to the half-inch mark and come back half a pencil length, half a pencil width. In other words, draw it at a half an inch and just draw it a little short. Close enough. It's going to come out right on the money, right? And if you can't see it from Montana or outer space, that's close enough. Okay, if you can get down to the nearest 16th, when you're doing conduit, when you're doing motor calculations, we're doing impedance calculations, if you get down to the nearest 16th, that's close enough, trust me, okay? So here we are. We found how long between the bends, 33 and almost a half inch. And if we mark it on the pipe, we're going to put our first mark there. We're going to go out 33 and a half. And just before the half mark, we're going to put a pencil mark. Just before. So it lays just inside the half inch. That's going to be close enough. And that's a good example of how to use this stuff. Now, the other example is when we're looking at any kind of a AC calculation, nothing adds up. Let me give you we talked about in the past where we had pure DC resistance. I think we talked about that today, didn't we? And we have when we wind a coil in some wire, it creates what's called inductive reactance. And we call that X sub L. And it takes, as I said, it takes a split second to a second, maybe 2 seconds sometimes, to build up, depending on the time constants. It takes this a little bit of time to build up. But the result of those two together we call impedance. And those are the letters we use to represent those things. And because it's always a triangular relationship like this, we need to apply this stuff because everything in AC does not add up directly. It's added up with triangles. Okay? So let's do one of these. Now I want to show you one thing, and we're going to get a little bit out there. Okay? We're going to talk about a motor. We're going to say that it has, now X sub L is in ohms. What did it say that reactance, inductive reactance is measured in? No, not ohms. Inductive reactance is ohms. Henries, that's reactance. That's the reactance itself. But the X sub L is measured in ohms, so it makes it a little confusing. But so let's say that we have this really long winding of wire, and this winding of wire is actually a couple of windings of wire that are connected together, and we call those windings a motor. Whoa, what a concept. And let's say that that motor winding has 10 ohms of resistance. Now, we can't tell, there's not a way to directly measure X sub L. Did you know that? But what have we said that we can figure out? If we have an electrical circuit, an AC circuit, remember we talked about apparent power and true power? If we see what voltage and current goes in, what do we call that? Apparent power, right? Okay. What do we see when we get our, well, when we change to AC, we're going to get rid of our R because we can see now that it's not just R in AC circuits. There's something else happening called X sub L. So now we have P, T, apparent power, total voltage, total current, and impedance. Now let's say that we have, let me figure this out real quick. Let's say that we have a 120 volt supply or motor, and we have a total, now we can, if our total impedance was 15 ohms, what current would we see? 120 divided by 15 is what? Right. So if we had 8 amps of current flow, wait a minute, isn't there a single phase AC motor that's 120 volts and has 8 amps of current flow? Somebody say yes. Yeah, there is. Okay, so this is kind of a thing. So we found our 15 from dividing our 120 by our 8 amps because those are things we can actually read. Our impedance, we have to infer, we have to divide. We have to assume that if we have 120 volts and we happen to have 8 amps of current flow, then our impedance must be 15 ohms. Okay, if that's true, then my impedance is 15 ohms. I can use my meter to read the pure resistance of the circuit, right? Now this is true of any circuit, not just a motor. Any AC circuit that has a winding in it and a coil, a transformer for instance, has impedance. Okay? So now from that we can back into how much, we can infer how much inductive reactance we have, right? Because now we know some things. What do we know about angles again? Oh hell, another hour of agony. Sine, cosine, tangent. Oh hell, another hour of agony. And what do we have here? We have side adjacent. Wouldn't you agree to that? This is the one next to it. And we have the hypotenuse. Wait a minute. We have a name for that. It's called the cosine. Now we're going to learn something new. What if I have two of these functions? but I don't have the angle. Can I get the angle? Just pull out that handy dandy TI-30X2S, and we're going to hit clear a couple times. And now we're going to do something new. We're going to do something new. We're going to hit second function, and we see that the cosine of this thing is 10 over 15, right? And that's a fraction, right? We're going to just put it in just like that. We're going to hit second function cosine, and it gives you a left parentheses, doesn't it? Okay, let's put in 10, because that's the adjacent, divided by, and put in divided by, 15, right parentheses, which you don't even really have to put in, but we're going to anyway. Now hit enter. Say again. 48.19. And what do you think that is? 48.19, and there's some more numbers out here, degrees. This is a right angle triangle. This right here is our right triangle. Our 90 degrees right over here. So it's 48.19 degrees. And from that, we can find out other things. But wait a minute. We said that this thing has a certain amount of power, right? Let's take this. We're going to multiply up. 8 times 120 is what? 60? No, it's not. Bad habit. Only Edison would say that's watts. That's VA, volt amps. That's apparent power, what's coming in. Okay, and that brings us to our real question. If we have a phase angle of 48.19 degrees, that's still on our calculator with a long number, right? That's still the cosine? Okay. So what we're saying here is that's the same angle as our power triangle. Except now we have 960 is our apparent power, which goes up here where the hypotenuse is. And what's down here on the bottom? You know what we call this down here? The result of the resistance is the real work that's getting done, and we call that true power. And because of that, this angle is called the power factor. The cosine of this angle is the power factor. It's going to turn, well, let's take it's 48.19 degrees, right? Okay. Let's hit cosine second function, answer enter, and tell me what fraction that was again. Okay. Hit clear. Just hit clear. Okay. Hit cosine 48.19 degrees. Enter. Just 48.19. Enter. What's it say? 0.6? That was our cosine before, wasn't it? 6.600? Oh, okay. So that's our cosine. That means that this circuit is 66.66% efficient as a circuit only. Okay? It had a circuit power factor of 66 because we multiply this fraction times 100 times 100 to get our percentage, right? So it's 66.66% efficient. So that means that out of this 960 VAs, we're going to multiply. Now we've got 0.666 in our calculator, right? Multiply times 960. Hit enter. $639? Is that right? Okay. So out of all this power that's coming in, it's only turning 639, turning it into 639 watts of real work. Not terribly efficient, right? Not that bad, but not terribly efficient. And in the second semester, we'll learn how to change that after we learn how to work with this a little more. But that's all we want to talk about today, because all of this stuff about the second triangle, you don't need to know that yet. But I just want you to know where we're going with all this. This is a tease. Isn't this going to be fun?